Cool. So myself, Ankur, and I work here as a staff engineer. The talk is about the Exoplayer, mostly Exoplayer as a framework, and it mostly focuses on how to do video streaming efficiently with Exoplayer. So there are going to be two focus areas in this talk. One focus area is mostly focused on how to treat Exoplayer as a framework rather than a library. Most of us see Exoplayer as a library where we can just give a URL and it will play whatever we want to play. The other one is to how to customize this, debug it, and how to build a solid observability over it so that we can see how it efficiently fit in our product rather than our product being fit into Exoplayer. So before starting, I want to ask how many people here have some production level experience of working with Exoplayer? Quite a lot. Good. And what about hobbyists? Like how many have some experience of working with Exoplayer? Cool. Okay. So what we are going to discuss, so we are going from fundamental to deep dive. So that's why we will first discuss about what is media, then we will discuss how the media flows on network, and then Exoplayer and debuggability and observability in order. So in the end, this is all component we are going to discuss. So it's going to be a lot of theoretical, and we are just done with lunch. So please buckle up and don't be too sleepy. So any playback system has primarily three components. One is media, what is getting played. The other one is network, how basically media is being transported. And the third one is player, who actually plays the media. So we'll discuss these three components in order. So first one is media. So there are a lot of layers in media. We'll go bottom up. So first layer is codec. So in the end, whatever we see or listen, it's just a stream of 0 and 1s. But before, in order to make sense out of it, it needs to be compressed in some form way to standardize it. So that's the role of codec. The codec gets bundled with tracks. So tracks could be an audio, a video, or a subtitle. So those are tracks, and then those tracks get bundled in containers. We'll discuss about all these in detail later. And then the containers are getting transported over network using some protocol, and then all four layers makes up a media. So let's discuss codecs in depth a bit. So codecs are just the algorithms which basically compress and decompress. The raw audio and video stream. There are a lot of codecs, but we'll discuss primarily about three codecs which are very famous. One is H264, which is also called ABC. I think a lot of you have already heard about it. It's kind of a universal hardware-based codec. Almost all the devices in the market, every TV, every phone supported on the hardware very efficiently. So if you have a very simple use case, this is the go-to codec for that. The next is S264 codec, which is called HEVC codec. This is the next generation codec of S264, and this gives 30 to 50% better compression optimization over S264. So what does compression optimization basically mean? That we are able to compress more video in the same amount of data, and this basically gives us a very good opportunity to save on the data uses of the customer. And also, since we are able to transport very less data on the same bandwidth, we also get to optimize on load time, buffering time for the user if we use this codec. So this codec is mostly used by almost everyone. We also use this codec in Glance, especially since it's also supports 4K videos. The next codec is AV1. This is introduced around 2020. This is a very developing codec right now. So one thing I forgot to tell about S265, there is a lot of complication about the royalty and the licensing of S265. That's why a lot of people don't prefer to use it. And that's where the AV1 comes. AV1 provide again a 30 to 50% better compression ratio over S265, and it is also royalty free. So you see, from S265 to AV1, this was introduced in 2000. This is 2020. In 20 years, we have achieved almost 100% of the better compression ratio. So That's why we are able to see a lot of high resolution content on a mobile in last 20 years. The next one is tracks. So tracks is very straightforward. These are audio, video, and subtitles, codecs bundled together. Each track is encoded independently of the other one. They can use their own compression algorithms. And when we bundle the tracks together, they become containers. So again, the containers are the algorithm which synchronize these tracks with some metadata timing and some timing information. And the three mostly famous tracks which almost get used everywhere are MP4, FMP4, and TS. I think we almost, a lot of people already might be using these containers. MP4 is again kind of a universal container where it gets streamed as a binary file over the network, and for a lot of very simple use cases, MP4 is the codec going to go for. Then the next is FMP4, which is optimization over MP4. It is a fragmented MP4. We will see in next slide more detail how to compare this. But FMP4 is the go-to container for a lot of adaptive streaming protocol right now for HLS and Dash. This is the golden standard that getting uses. And the other one is TS. This is more older than than MP4. This was originally developed for broadcasting system, but then it was adapted by Apple for live streaming in HLS. So this is how a TS container look like. There's a header, there's some flag, and then there's a payload. And then there's another TS segment, then there's another segment. So the idea here I want to show is basically that there could be multiple TS appending to like one after another, so that we can have some kind of adaptive streaming using these TS. This is how the MP4 and FMP4 look like. In MP4, there are few headers and then there is a big block of data. While in FMP4 there are few headers, then there is an individual header for each block of data. So what I'm trying to tell here, that if there is some congestion in network or there is some error, the player has to restart from here. In order, earlier like it was playing here, then if there is some error occur, player has to restart. While in FMP4, it can restart from any middle point. So that's the flexibility that FMP4 provides, and that's why FMP4 is one of the major base for all the streaming protocol in the market. Next is protocol. I've been talking about protocol for some time now, I think. So protocol is just a contract in between the player and the media, which tell how the media will be delivered to the player. And these are mostly open standard, which are followed by almost everyone in the industry. So I have mentioned 4 very famous protocol. First one is progressive download. This is the simplest form of the protocol in which a single MP4 file is delivered over network. And since it is the simplest way of media streaming, this is almost used in every ad platform, because ads are very small and they have to be played in almost all the devices. So due to the simplicity, ads use this progressive download protocol. The other one, the next one is HLS. This was introduced by Apple to revolutionize the live streaming industry. It basically uses a TS fragment or a FMP4 fragment to deliver the content under a M3 playlist file. We will see later what is M3 playlist file. But HLS is great for live streaming and adaptive streaming. The next one is Dash. This is the I think most of the 90% of streaming that happen in current world happen over Dash. This is an open standard for all the devices which are not Apple. So Apple devices, HLS, non-Apple devices, Dash. This again uses an MPD master file with FMP4 segment under it. The last one is RTC, which is basically used for video conferencing, real-time protocol. This happens over WebRTC. We might not be talking about live streaming that much in this talk to reduce the scope. But yeah, it's itself in its way. So adaptive streaming. So I think whatever content we consume over any media platform, whether it is Instagram or Netflix, everyone uses adaptive streaming because it guarantees that the video will play. If the user has some internet, the video will eventually play. So that's why everyone uses adaptive streaming. It basically allows the player to switch dynamically between different quality of videos and audios to adhere the current network condition and the device constraints. Basically, one big file is being divided into a small file of different resolution and transmitted over some adaptive stream protocol, either HLS or Dash, so that player can adjust dynamically based on the constraint. So this is how, on a very high level, adaptive streaming look like. There are multiple chunks of files in different resolutions, and based on the network speed, the player chooses which chunk to play at the given moment. So you can assume there are multiple copies of the same content in different resolutions. Player keep on jumping between those resolutions based on the current bandwidth of the internet. So let's discuss some detail about HLS. So HLS is very simple, very simple protocol. So in this talk, you might listen about simplicity and customization. So there could be a lot of use cases where you will prefer simplicity, and there are a lot of use cases where you will prefer a lot of customization. So it depends on the use case, what you are looking for. For example, I talk about ads. Ads need to be very simple, so they need to go for the very simplest protocol. So HLS, as I was talking, is very simple adaptive streaming protocol. And that basically guarantees that the live streaming that happens over HLS is very low latency. So it looks like there's a M3 unit. This is the M3 in master playlist, which has reference of other playlists of different resolutions. And these playlists have reference to actual media, which is being fragmented into small parts, which could be FM4 or TS. This is Dash. Dash is a little bit more complicated than HLS, and there are a lot of use cases which can only be solved using HLS, but not by which can only be solved by Dash, not by HLS. So this is how a typical HLS Dash content look like. It has an MPD master playlist which has period IDs. So these period IDs could be different kind of media. It could be just one movie here, other movie, then ad, then second ad, and then other movie. So basically, you can inject a lot of different content in the same video file, same video. Then a particular period ID point to an adaptation set. Adaptation set could be a subtitle, a video, or a audio in English, or a audio in German. And then adaptation set will point to representations. Representations are just content at different kind of quality, different bitrate basically, maybe 1 Mbps or something. Then a representation set point to a segment, which is a kind of a container, and then this container point to FM4, which has the fragmented media segment itself. So we talk about HLS and Dash till now. So what happened? Still, it's happening in this industry that if you have to support Apple devices and non-Apple devices, you have to build two things: one Dash and one HLS. This results in twice the cost of storage, twice the cost of maintenance, and twice the cost of team to optimize those platforms. So this leads to a lot of carbon emission also. So that's why industry took an initiative to somehow reduce these costs. And then come the CMAF. This is a very evolving protocol, which is a kind of a wrapper protocol over Dash and HLS. So what does it have? It has a wrapper over a Dash and an HLS M38 and MPD master playlist, and both get pointed to some same FMP4 file. So basically, it solves for the problem where you need to have separate copies of FMP4 Basically, if you create one CMAF file, you can that CMAF file will have a MPD also and will have a M thread also. So if your device is Apple, it will pick the HLS from that and point to those FMP4 segments. If your device is non-Apple, it will pick that MPD and point to same FMP4 segments. So I think you got the idea. We just reduce the cost by 2. In class, we are using this particular format, and this basically reduces a lot of cost for us. As I was telling, CMAF looks like this. So it has a wrapper over both M3 and MPD, which point to same FMP4 segments for audio, video, and SRTs. Cool. So we covered one part of the talk, which was the media. Next is I hope people are with me. Next part is network. So network dictates how this media reaches till the player. And the most important part of network is the protocol, where the networking is happening. There are 2 protocols from ages. One is UDP, HTTP, and TCP. I think you can recall from your college days learning those protocols. And it depends which HTTP version you are using. Either TCP will pick or UDP will pick. So till now, till 2018, most of the industry were using HTTP 1 and 2, which is based on TCP. Then Google came up with their own version of new protocol, which they call Quick, which gets standardized as HTTP 3, and that work on UDP. So we'll see why to use Quick. And if you use Exoplayer, by default, it uses a data source which supports HTTP 3. So if your CDNs, your server support HTTP 3, the Exoplayer will automatically start using HTTP 3. So these are some points to basically justify why to use Quick HTTP 3 for media streaming. As I was telling, it was developed by Google and then standardized as HTTP 3. It work on UDP. So in TCP, what happened? There is a 3-way handshake before any connections establishment that happen, and that takes a lot of time before any real data get transferred. So Quick solves this by having UDP, which only need 1-way handshake. And if you are able to tell your player that I know this particular domain, they support HTTP 3, don't go for handshake, start emitting data at the same point. Then we can achieve 0 RDD also. So from 3-way handshake, we came to 0 handshake, and the data can start transmitting as soon as possible. So it gives a lot of startup time benefit due to this. So then the obvious question comes: why industry was not using UDP before? If UDP is so that great, because UDP has a lot of fault. It's not very fault tolerant. TCP is very fault tolerant. That's why people are not able to use UDP. But Google solved it, the Quick solved it basically to build their own retransmission and fault tolerance stack in Quick, which solve this problem of reliability. So we have experimented with Quick, and what we see that as our latency is reached to P95, the Quick perform 50% much better than the HTTP 2. And why it happens? So basically what I'm trying to say is that worse the network, better the performance of Quick over HTTP 2. And why it happened? It happened due to this head of line problem, which is there in HTTP 2. So what happened in head of line problem? That a packet which is in front of the line, all the packet follow that particular packet. And if due to any problem, maybe you are traveling in bus, you are switching towers, or maybe you are switching from Wi-Fi to mobile network, that packet will get lost. And if that particular header packet will get lost, all the packet following that packet will get lost. And you have to re-establish that connection, you have to retransmit everything from beginning. And Quick solved it by not doing head of line implementation. It has its own stream for individual packets. So if a packet gets lost, that particular stream gets lost. Cool. So till now we have got the second part also, which is our network. So media is done, network is done. I don't know how much time is left. Okay. Okay. Cool. Then come the Exoplayer. Actually, what we were supposed to talk about. It has 5 main components. render factory, TrackSelector, bandwidth meter, load controller, and media source. So basically, what this component gives us, they provide a lot of customization. We can override a lot of code inside it, and then we can see what fit in our product. So first is render. What is render? So render is basically responsible for decoding of the actual codec that is coming as part of media. So what get output on a surface or in an audio sync or on a text box as a subtitle is governed by render. So by overriding render, we can do a whole bunch of animations, clipping, visual effects in our video. We can apply a lot of filters. We can do OpenGL kind of stuff that I was talking about earlier with the help of renderer. We can intercept the frames. We can apply ML models for some identification in those. So let's say I want to identify if a person is very close or not. I can use renderer to give me frame, and then I can give it to an ML model which do that classification. And also we can do a lot of subtitling related customization also. The next is TrackSelector. So TrackSelector is responsible for choosing media tracks out of the stream. So we have to play 720, 180, 1080, or what kind of audio, English, Hindi, what need to be played is governed by TrackSelector. By overriding the functionality of TrackSelector, we can customize all those logics. We can customize, let's say we want to play 720 on mobile data, 1080 on Wi-Fi, we can do that. We can customize that always start from the lowest bitrate possible, so that the load up time is very less. We can do that with the help of customized TrackSelector. We can give user. I think we all see Netflix. There is a option to switch between the video quality. That is something which is governed by the TrackSelector. Then next is bandwidth meter. So bandwidth meter is a component which keep track of the actual bandwidth of a user. What is the network speed that user is experiencing. So it keep track of what was the resolution of the video, bitrate of the video that get downloaded, and in how much time it get downloaded, and it keep on taking our average, and that's how it is able to keep track of the actual user bandwidth. And whatever we need to do from user bandwidth, those all customization we can do with the help of TrackSelector. For example, we can inject our own algorithms. Maybe let's say we want to have different algorithm of heuristics for mobile, for Wi-Fi we want to have different algorithm. We can do that with the help of bandwidth meter. The next one is load controller. This basically manages the buffering of data. How much to buffer? Is it enough? Have the player buffered enough? And should I stop buffering now, or should I keep on buffering? How much should I buffer just to start the playback? So there are 4 key values which we can tune, and tuning these values gives a lot of benefit in tuning the experience for user. One is min buffer. How much buffer need to be maintained at a given point in order to pause the video. Like before, if the buffer drop below that, the video playback will get paused, and it will wait for more streaming before continuing. Max buffer, it is to basically avoid over buffering or using excess memory. Buffer for playback, this basically tells how much need to be downloaded before you start playing the video. So if you keep this to a lower value, you will be able to get a lot of quick video startup time. Then the playback, buffer for playback reset after rebuffer. This basically tells if there is a rebuffering happening, how much to ensure before restarting the playback. So you can go through a documentation, but yeah, tuning these 4 values can give you straight out of the box benefit in your playback. Then comes the last part of Exoplayer architecture, which is media source. So media source are the one which defines basically how the media is downloaded, passed, and exposed to player. So this is actually doing that networking kind of operation. So each playback item has a media item which wraps a media source under it. There can be different media source for different kind of protocols. Progressive, we talk about HLS, Dash. So media source can also be wrapped around a cache data source for having offline kind of a capability. If you see there are There are a bunch of download option in YouTube, Netflix. All those are implemented using cache data source. If you scroll your Instagram, you see a lot of video very quickly load. That also implemented using some sort of cache data source only. So it takes two sources underneath: upstream data source, which basically download the media from remote, and the cache data source, which basically pre-buffer or post-buffer that media. We will talk about one more component. So this is the media source that we talk. So preload manager we'll talk later, and priority task manager we'll talk later. But yeah, media source looks like this. Is a media source, which is a media item. It can have different kind of media sources, which will wrap cache data source under it, which will wrap upstream data source and a cache in a local disk cache. And upstream data source, we talked about HTTP3 before, so it will wrap that, and it will wrap a priority task manager that we'll talk about. Cool. So preloading manager, it's sort of part of media source only. So the real kind of experience that I was talking can be implemented using preloading manager. What it gives, we can basically have a pseudo kind of a player before actually playing the video. So we can tell the preload manager that this is my URL, preload this, and we can customize the preload manager in order to tell how much to prefetch. Let's say I want to prefetch only 2 seconds of that video, and when to prefetch, and control maybe delaying the prefetch or suspending the prefetch. All those kind of things we can do using preloading manager. I think it is just released last year, I guess, since a lot of short videos was coming in market. And before this preloading manager, I remember we have to do a lot of own customization in order to improve the startup time. But yeah, it's become very handy after this particular API. Then comes the priority task manager. So since we are doing a lot of loading, we might have a lot of video players. Maybe if we visualize Instagram reel, there's a video player X. Before that, there's a video player there, video player at the bottom also. How do we prioritize which one to buffer, and where to how to queue these the buffering of media sources? So that queuing behavior is provided by priority task manager, and we can provide the same instance of priority task manager to all the media sources of those players, and using this priority task manager we can tell which one to prefer, which one is lower priority, and to suspend. We can do things like pause or deprioritize the background task using a priority task manager. We can dynamically adjust the priorities of the video. Let's say user scroll and it comes to this video. We have to deprioritize the other video. That can be done using priority task manager. Error handling. So this is also one of the more very low hanging fruit. Tweaking error handling policies, we can drastically improve the video experience of user. We can tell how to respond to a particular error. Either that error is recoverable or not. We can catch those errors. We can on the basis of error codes, we can particularly tell that this is a track selection error. Let's do a different track selection. This track is faulty. Or this is a rendering error. Let's not do audio rendering. Let's only do video rendering. Maybe the audio track is faulty. So all those kind of error handling we can do, and the most important thing, we can log all those analytics. So we get those data. We see that, for example, a lot of videos are playing with faulty video track, but audio track is fine. We will get to know that backend is maybe compressing wrong video or using some wrong codec which are not supported for this particular device. So using all those analytics data, we can dig down how to improve the user behavior of our videos. Yeah, so we are done with the architecture of Exoplayer part. The next part is debuggability. We will see, so these are few of the callbacks which are out of the box from Exoplayer. In the next session, we will see how to use this data in order to build an observability. But yeah, let's go to these callbacks first. So the first is on render first frame. This will tell how much time the video takes in order to render the first frame. The playback state change is the video playing, buffering, or ended. the play when ready change, if the user is playing, pause the video, background foreground side kind of a behavior. Playback error, we talked about it just before. Input video format change. This will tell us what is the resolution of the video that user is watching. On device volume change, this will tell if the user is watching on mute or unmute. And the network transfer display. This will tell us what is the speed by which we are able to download the video of the user. Cool, so this is the last section. Whatever we talk about talks a lot about customization of Exoplayer. But if we are customizing a lot, but how to see if our customization is working for user or not? So we need to have some kind of observability before tweak. Let's say earlier I was a S264 codec and I want to shift to S265. But how to basically judge if that change work for some user or not, or for which user it work, for which user it's not working. So we have to build some way of observability which we can observe continuously on data and do a very continuous experimentation on player. So this is a very famous framework provided by Mux, which is a very open source video contributor. They provide 4 kinds of scores. One is playback success score, startup time score, smoothness score, and video quality score. These scores are rated between 0 to 100. They have their formulas, and using those formulas, we'll just have a quick look to those formula in next slide. But yeah, by observing all these 4 scores, we can do all those experimentation and customization which we talked about in this particular talk. So first is playback success score. So what is 10? It simply rate if the user was able to see a particular video to the 100, if it exits before 1 second to 50, if the video failed with some error to 0. And by averaging out these values for all the users, we will get a score between 0 to 100. And we will be able to see here, our videos are encoded properly and almost like what percentage of users are able to see our video. If the score is high, the playback is reliable. If the score is low, there is some error in encoding of the videos. The other one is startup time score. This basically tells how quickly we are able to load the first frame of the videos. The load controller I was talking about, we can tweak those values and we can observe this particular score. So the formula is very simple: 100 into 1 minus startup time divided by max threshold. So you can decide the max threshold value according to your use case. We follow 5 seconds for this. So if the user is able to load the video is able to load within 5 seconds, that's for example in 1.5 if it loads then the score is 70. So that's how we can get the values for all the users. And if the score is high, which means the user is able to see our video very quickly. If the score is less, maybe video experience is not that great. The third is smoothness score. This is basically the rebuffering that happened in a video. For example, we see YouTube and then we see a loader. How to observe those kind of behavior, how to rate those kind of behavior. So we define a formula. So 100 into 1 minus 0.7 to rebuffer percentage. And so basically these values you can decide on your own according to your use case. But the main values are rebuffering percentage and rebuffering count. Rebuffering percentage is just the total amount of time spent by user in watching that loader, rebuffer loader, divided by total time spent by the user on that particular video. And the count is how many times the user sees that loader on the video. So that's how we will get to a score between 0 to 100, and we will be able to justify the behavior of user, the experience of user. The last one is video quality score. This basically tells that the quality that we are showing to user is good or not. If the user is able to see high quality content or not. This has 2 values. So basically this talk about upscaling value. So let's say a device is able to render 1080 pixel, but we are serving user, but due to some problem user is able to see only 720 pixel. Then there is an upscaling happening at each pixel level, which is basically 720 divided by 1080. So that's the upscaling percentage. So we put those percentages, the max upscaling that happened in one session, and the average upscaling that happened throughout the session. We can put those values in this formula and we'll get a score of between 0 to 100. And again, if the score is high, the users are seeing crisp videos. The score is low, the videos are blurry. So this is a summary, this is the last slide. We talk about 4 scores, and using those scores, we can continuously iterate on our video experiences. If the video experience is something which is important for your product, these 4 scores helps a lot in order to justify what actually user is watching. Cool, that's all. So this is my LinkedIn handle, and these are my email IDs, personal as well. I want to just say that we are hiring across Android and iOS. So you guys, if you can send me, if you have friends or you yourself looking out, you can send the resumes to me, and we will see if there is some role that fits your resume. Cool. So, any question?
Yes.
Yeah.
How ads are inserted means while encoding or?
Cool. So we omit 2-3 things from this. One is live streaming, the other one is ad, the third one is DRM. We didn't cover those topics due to the constraint of time. But ads are inserted using if you take a sense of MPD, you are seeing in this slide. So in this slide, you see these period IDs. This period ID is nothing but a different kind of content inside one content. So this period ID 2 could be in one ad. This period ID 4 could be one ad. So this the server can encode itself the ad before even serving content to user. Or if we have some client side ad SDK also. So Exoplayer provide out of the box support for Google Ad SDK, which can insert ads in between at the given time. But they are not that optimized compared to the ad inserted in the MPD itself.
You spoke about media source, where it does caching also. So how to basically find out whether the media is playing from upstream or from the cache source?
So we have a network transfer listener that I talked about. So in this we get a callback and which have a flag that this is being served from cache or network. There is a direct flag.
Okay. Now suppose a downloaded video, if we are trying to play with the Exoplayer itself, and we just give it the source key where to download it from. So once video is cached, will it still fetch from network or it will use the cached one?
No, it will not use.
Is there any strategy we can set okay, now you have to pull from network or use only local?
So generally what you do, you wrap your network data source inside a cache data source and give a cache instance to this data source. So when you provide this particular data source, it will take care of downloading on demand automatically. So it will first see if the content is available in cache or not, and not basically it takes some eviction policy also where you can define when the cache is full, where to evict, how to evict, which one to evict, and it will automatically take care of not downloading from basically network if the content is already there.
What about the expiry key when that content should be deleted?
Yeah.
That handling.
So this cache take a eviction policy.
Okay.
It's an instance of class where it has some eviction policy based on the cache total size, but you can also write your own custom eviction policies.
Thank you.
Last question, we'll take yours later to run any shorter time.
So you spoke about HVEC.
Yeah, I'm audible.
You spoke spoke about this HVC format, right? We had a little bit of trouble there because we were to serve X265 format to the. So we developed something like a real style of feature where we have to serve HEVC on the play, and we chose to do it with binary format instead of streaming format because our videos are more or less 10-15 seconds. Certain devices, low-end devices, still does not support HEVC. They still rely on H264 format. So transcoding cannot be done on the device, right? Because that takes a lot of time. Let's say 5-10 seconds. Though from Android 12 we have support for on-device transcoding, that's not something that we didn't do. So we went ahead, took a safe route of just sticking to H264 because this is just binary and we're not going to deal with anything complicated. What would your approach be? Do we have to compromise the low-level users
Yes.
and just ditch them and right?
Yeah, so that's what I was talking about, the simplicity versus customization and optimization basically. For example, I was talking about ads. Ads has to target everyone. They cannot choose for HLH and all these fancy things. They have to go for the simplest possible. In the simplest possible, the universal format is H264, the universal container is MP4. Those are the two things which are universal.
Another question is regarding the cache data source. So, cache data source is actually disk read and write. It's not in-memory read and write. We tried doing something in memory, that is like keeping that, in-memory thing, not actually touching the disk or reading it from there. So, yeah, I mean, it does give out some level of latency, like a few milliseconds. But is that still considerable, or can our own custom in-memory data source would still serve the purpose? The video is going to be just 10 seconds.
So that's what I think preload managers solve for. That's what I talked about. So earlier we had to do all these techie things that you told.
We're still doing it manually.
Sorry?
We're still doing it manually.
Yeah, you can replace it by preload manager.
Okay.
Now, preloading manager. It simplify all those APIs. It's make a sort of a fake player. So the player is not there, but you can initialize all the track selection, all the load controller and media sources, and do all the customization you want. And then later ask that same manager to give you the instance of player which you can play when the user actually reaches to that particular video.
Okay. Thank you.
Cool guys, so we'll proceed with the lightning talk. Sorry, we can't take questions. We'll take later because we're running out of time.
I am here only.
Yeah. Thank you, Ankur.